evening, guys. I hope you're well. So this is our first lesson in physical sciences. Today we'll be doing the scientific method. Before we get started going deeply, I just want to explain a few key terms. It's just two terms, which is hypothesis and scientific theory. A hypothesis is a proposed explanation for an experiment. So this is a statement of the outcome of what you expect your experiment to bring. So it can be anything from, it can be right or wrong, basically, right? That's your hypothesis. An explanation of your experiment. Now, number two, scientific theory. A scientific theory is a theory that has been tested and proven through repeated experiments and data. Okay, so now that we've explained those terms, you'll be seeing them a lot, so just make sure that you understand them. Remember, a hypothesis is a proposed explanation of an experiment, and a scientific theory is a theory that has been tested and proven through countless repeated experiments and data. So let's just break down physical sciences. Basically, physical sciences constitutes of physics and chemistry. All sciences use experiment and testing to understand the world better around us. The scientific method requires us to constantly re-examine our understanding by evaluating new evidence with current theories and make changes to those theories in the evidence if the evidence does not meet the test. Therefore, the scientific method is a crucial tool you will use throughout physical sciences. Remember, guys, theories are not fixed, so which means that every time there's new data or a change in the experiment results, a theory can change. Hypotheses are formed and tested, leading to scientific theories explaining the observations and predict results. Results are not tampered with to fit the hypothesis. Remember, a hypothesis can be either true or false after the experiment. New information is taken into account when improving and expanding current theories. Okay, so now we'll just give you a breakdown of the scientific method, which you should familiarize yourself with so that you can be able to use this to make your own experiments at home. Remember, your first step is to ask a question about the world around you. What do you see around you? Do background research on your questions. That's your number two. Number three, wait guys, I just want to rotate, these notebooks. All right. Number three, you make a hypothesis about the event that gives a sensible result. You must be able to test your hypothesis through experiment. Design an experiment to test the hypothesis. That's your fourth step. These methods must be repeatable and follow a logical approach. Collect data accurately and interpret the data. You must be able to take measurements, collect information, and decide whether your hypothesis explains the data collected correctly. If the data fits your hypothesis, verify your results by repeating the experiment or getting someone else to repeat the experiment. Number 8, if your data does not fit your hypothesis, perform more background research and make a new hypothesis. Okay, so now this is how you approach your experiment. First, your first point is your aim. So that's a brief sentence describing the purpose of the experiment. Your apparatus is the list of apparatus that you will use to make your experiment. For example, you can use a beaker, your testing tubes, and everything like that. Method, that's your number 3. A list of the steps followed to carry out the experiment. Number 4 is your results. Tables, graphs, and observations about the experiment, as you've illustrated already. We'll be going to over these in a short space of time. Okay. Yapel. Okay, sorry please. Discussion. What do your results mean? Conclusion. A brief sentence concluding whether or not the aim was met. Okay. So yes, that's your overview of what a scientific method entails. So now we'll just play you a brief video that will basically illustrate what we've been discussing so far. Okay, guys, now that you are back, let's just discuss how to basically plot your results. So basically, as you can see, we've got two graphs here. Let me just open notes quickly. So these are the features of the graph that you will plot always. This is where you can get your extra marks, free marks, that's what I call them, so that you can be able to actually pass your studies. So yeah, as we were saying, when you're plotting your graph, make sure that you use an appropriate scale so that the plotted points use most of the axis space. Work out the range of the data and the highest lowest points and lowest points. The scale must remain the same, guys, along the entire axis, and should use easy intervals such as 10s, 20s, 50s. Use graph paper for accuracy. Each axis must be labeled with what is shown on the axis and must include the appropriate units in brackets: temperature in degrees Celsius, time in seconds, height in centimeters. Remember to use IS units. The independent variable is generally plotted along the x-axis. Remember, this is the x-axis, and then the dependent variable is plotted in the y-axis. Okay. A best fit line is then added to the graph. So let's say maybe you've plotted your points. Just make sure that you draw your best fit line. Do not start the graph at the origin unless there is a data point for 0 to 0. So this means that if maybe your lowest point is around 500, you can just get them to cross like that, and then maybe you can say 500 here, and then maybe here you can say 300. That's how you actually start the graph. That's why you need to just start your graph where as I was saying, guys, do not start the graph at the origin unless there is a data point for 0, 0, or if the best fit line runs through the origin. The graph must have a clear descriptive title which outlines the relationship between the dependent and the independent variable. If there is more than one set of data drawn on the graph, a different symbol and or color must be used for each set, and the key legend must define the symbols. So let's say maybe you want to have another second graph here. You can just color this one differently, or maybe just use a dashed line like that and have your legend here, which will basically explain what this line represents and what this one represents in this example. Use line graphs when the relationship between the dependent and the independent variables is continuous. For a line graph, you can draw a line of best fit with a ruler. The number points are distributed fairly evenly on each side of the line. With an exponential graph, you can draw a best fit line freehand. So for example, in this case here, as you can see, the graph shows that sort of exponential rise. So after plotting your points, you can just draw this line freehand. Okay. All right. So now let's look at data analysis. Uh, Basically, we have two types of analysis when it comes to data. We have qualitative analysis and quantitative analysis. In qualitative research, you look at the quality of a substance, at how it looks compared to other cases. You do an in-depth analysis of each specific case and then make an informed decision about similar cases. For example, a qualitative study of the study habits of university students could make only a few people, or over 20. Each person would be asked in-depth questions about how they study and what works for them, and a general formed assertion can then be made about these study habits. Okay, now let's look at quantitative analysis. Sorry. In quantitative research, you look at the specific numbers. You study a large group and do statistics. And do statistical analysis of the group with experimental controls, manipulation of variables, and the modeling and analysis of your data. For example, a quantitative of those same study habits of university students would include a large number of people for statistical relevance. The questions asked would include raw data of actual studying hours and the most productive study times. These data points would then be analyzed using graphical models. Okay, so since we talked about doing experiments, we need to look at safety procedures so that you can actually stay safe, because that's very important in science, to make sure that as you do experiments, you also stay safe. Your safety is very important. We still need you as a scientist, guys, so that you can be able to do these experiments and solve problems our world is facing. All right. Uh, so yeah, laboratories have rules that are enforced as safety precautions. These rules are: before doing any scientific experiment, make sure that you know where the fire extinguishers are in your laboratory, and there should also be a bucket of sand to extinguish fires. You are responsible for your own safety as well as the safety of others. Pause. So before doing any scientific experiment, make sure you know where the fire extinguishers are in your laboratory. In your laboratory, and there should also be a bucket of sand to extinguish fires. You are responsible for your own safety as well as the safety of others in the laboratory. Never perform experiments alone. Excuse me. Do not eat or drink in the laboratory. Do not use the lab. From now on, it's the lab, guys. Glassware to eat or drink from. Ensure that you are dressed appropriately whenever you are near chemicals. Hair tied back, no loose or flammable clothing, closed shoes, gloves, safety glasses. Always behave responsibly in the lab. Do not run around or play practical jokes. Always check the safety data of any chemicals. Before doing any scientific experiment, make sure that you know where the fire extinguishers are in your lab, and there should also be a bucket of sand to extinguish fires. You are responsible for your own safety as well as the safety of others in the lab. Never perform experiments alone. Do not eat or drink in the lab. Do not use the lab glassware to eat or drink from. Ensure that you are dressed appropriately whenever you are near chemicals. Hair tied back, no loose or flammable clothing, closed shoes, gloves, safety glasses. Always behave responsibly in the lab. Do not run around or play practical jokes. Always check the safety data of any chemicals you are going to use. Never smell, taste, or touch chemicals unless you are instructed to do so. Do not take chemicals from the lab. Only perform experiments that your teacher instructs you to. Never mix chemicals for fun. Follow the given instructions exactly. Do not mix up steps or try things in a different order. Care needs to be taken when pouring liquids or powders from one container to another. When spillages occur, you need to call the teacher immediately to assist in cleaning up the spillage. Care needs to be taken when using strong acids and bases. A good safety precaution is to have a solution of sodium bicarbonate in the vicinity to neutralize any spills as quickly as possible. If you spill on yourself, wash the area with lots of water and seek medical attention. Never add water to acid, guys. Always add the acid to the water. When working with chemicals and gases that are hazardous, a fume cupboard should be used. Always work in a well-ventilated area. When you are instructed to smell chemicals, place the container on a lab bench and use your hand to gently fan the vapors towards you. Be alert and careful when handling chemicals, hot glassware, etc. Never heat thick glassware as it will break. For example, do not heat measuring cylinders. When lighting a Bunsen burner, the correct procedure needs to be followed. Securely connect the rubber tubing to the gas pipe. Have your matches ready. Turn on the gas, then light a match and Bunsen burner. Do not leave the Bunsen burners and flames unattended. When heating substances in a test tube, do not overheat the solution. Remember to face the mouth of the test tube away from you and members of your group when heating a test tube. Always check with your teacher how to dispose of waste. Chemicals should not be disposed of down in the sink. Ensure all Bunsen burners are turned off at the end of the practical and all chemical containers are sealed. So guys, that's all we have for now on the scientific method. I hope this was informative and educative at the same time. If you have any questions, guys, you can just always ask on our comment section and we will be getting back to you as soon as possible. In the meantime, also make sure that you like, you comment and subscribe on our YouTube channel so that you can stay updated on our content. Thank you so much, guys, for staying this far with us. And as we say, this is our first video. There's more stuff coming, more amazing stuff is coming, and just stay tuned. Bye bye.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exact. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.